Now that we know how to differentiate our exponential, let's use it in some practical problems. So rates of change. So the exponential function, I guess one of the most common places you see it in a practical application is this idea of growth and decay. Now it starts, the very basic growth and decay model starts from a very simple assumption that your growth and decay is proportional to population. So the greater the population, the greater the number of people that will die or grow. The rate of change of the population to P to T, because it's directly proportional, will equal to some constant times the population. So there's our starting point. Oh yeah, not only populations, radioactive material, that all undergoes the same sort of decay model. The solution to this turns out to be P is equal to some constant times e to the kt. It is alright. If you see the P to T equals kp, we can say, yep, I know the solution to that basic equation is P equals ae to the kt. Let's have a look at an HFC question. So the amount of caffeine in the human body will decrease according to, and there's our basic equation again, to C to T is some constant. In this case it's a negative constant, so that tells me it's decaying, where C is measured in milligrams and T is the time. So what they often do, rather than getting you to derive the equation, so remember I said you're allowed to just quote it, but what they do get you to do, so there is some calculus involved, is get you to show it's a solution. So rather than starting with a derivative, start with the solution, differentiate the solution. So C is ae to the minus 0.14t. Differentiate exponentials, we differentiate the power. So that's going to be minus 0.14, but the power in this case doesn't change. So we get minus 0.14 ae to the minus 0.14t, which is minus 0.14 times the solution, C. So we have shown, yes, that is a solution. It does work. So now they've given us some conditions. When T is 0, we know there's 130 milligrams of caffeine. So now let's work out what A is. Well, when T equals 0, C is 130. It's really just a substitution question now. So A is 130. When you think about it, that constant A has to be the initial value, because that'll be when T equals 0. And so e to the power of 0 is always equal to 1. Constant will be the initial population, whatever that happens to be. So how much caffeine is left after 7 hours? All right, well, when T equals 7, we now know A is 130. Again, it's just a substitution question. So we get 48.8, correct to 1 decimal place. What is the time taken for the amount of caffeine in the body to halve? So when is C now 65? And amazingly, you get this equation. E to the minus 0.14t is equal to half. Now what it actually is, it's exactly the same as finding half-lives for radioactive decay. It's the same idea. It's exactly the same equation. Because we end up with, there it is, T is minus 1 divided by 0.14, whatever that is, the log of a half. And we get 4.95105. So right after 5 hours. 11F.